Welcome to our review of differential equations. We've got a lot of different things to go through, like solving just some pretty easy differential equations and then some harder separable differential equations, using slope fields, and then talking about exponential growth and decay and Newton's law of cooling. So get excited. This is going to be lots of fun. Okay, we want to, on this first section of things, evaluate the definite integral. So I kind of actually forgot to mention this in the list of things we're doing, but this is actually something you probably have already done before. This should be review, hopefully, if you're trying to learn about differential equations. So what we want to do is just integrate x plus 2 and then plug in 0 and negative 4. And when we plug them in, we take what we get when we plug in 0 and what we get when we plug in negative 4, and we subtract them. It's very important that you remember to start off by finding the integral. So that's the power rule. Since this is a polynomial, right now this is x to the first, and so I'm going to add a power, which gives me x squared, and then divide by my power. This plus 2, since it doesn't have an x right now, is going to get an x, so it'll be plus 2x. Then what we want to do is plug in 0, negative 4. So we draw a line and write down 0, negative 4 so that we all know that that's what our plan is as far as what we're going to do. And then we're actually going to plug those in. Now, whenever you plug in 0, if you realize that that's just going to be 0 because plugging in 0 into either one of these is just going to cancel out what we have, you could actually just skip ahead and write that that's 0 minus, and then we do need to actually work out what the other part of this is. We're going to do negative 4 squared over 2 plus 2 times negative 4. We can either do that by hand or in our calculator, and we just need to make sure that after we figure out what it is, that negative that's in front is still in front right here. So if what's inside the parentheses is a negative number, then it ends up being positive. If it's a positive number, it ends up being negative. If I do this, negative 4 squared over 2 plus 2 times negative 4, I get a really nice answer because that is actually 8 minus 8. And so since that's 8 minus 8, and that's 0, and this is 0, and 0 minus 0 is 0, our answer is 0. That doesn't happen super often that we get an answer of 0, but it did in this case. So we want to do another one. This one probably won't end up being 0. In fact, this one actually is kind of a jerk as far as figuring out what it is if you're not using your calculator, or if you're not good at typing these things in your calculator. We want to go ahead and integrate using the power rule. So this is going to change to a 3, and we're going to divide by 3. Since there's already a 2 on bottom, that's going to make that be a 6 on bottom. So this is negative x cubed over 6. This has a 1, so we're going to add a power, which gives us 2, and then divide by 2, which means those 2's are going to cancel. So that's minus x squared. And then this negative 1 doesn't have an x, so it's going to get an x. And we're going to plug in 1 and negative 4. This time, it's not going to be as easy. We have to actually plug in both numbers. What a pain. But I'm sure it'll be fine. So we're going to plug in 1. That's negative 1 cubed over 6 minus 1 squared minus 1 minus negative 4 cubed over 6 minus negative 4 squared minus negative 4. So this first part, and if you're doing it on the calculator, you just got to make sure that you put your negatives in parentheses and that you just type it in exactly how it looks right here. If you're doing it by hand, we can say, okay, well, negative 1 cubed over 6 is negative 1/6, and negative with the 1 squared, since it's not in parentheses with the negative, that would still be a negative 1. So these add together to get negative 2. Then we can work on this section of things. Negative 4 cubed is negative 64, but the negative right here would make that positive 64. So we're having 64 over 6, which would simplify to be 32 over 3. This negative 4 squared makes it positive 16, but there's a negative in front, so that makes it minus 16. You square the negative and then put what's in front. You don't cancel the negatives out. That's not what's happening, because the negative 4 is in parentheses, so it has to deal with the squared first. Here, though, these do cancel because there's not a power with negative 4, so that's plus 4. Well, that means that we've got 32 over 3 minus 12. And so it's at this point that if you haven't already grabbed your calculator, you would probably want to. This ends up being the negative 5/6. And so you can go farther with getting like common denominators and things like that and do it by hand. Or if you're allowed to use your calculator, you can use your calculator and save yourself a little bit of a headache probably. Now, in this next section, what it's doing is it's testing whether or not we remember the fundamental theorem of algebra. I feel like I should have like a voice box to make that sound even cooler, but I don't, so we'll just leave it as is. What we're trying to do is find f prime of x. You should hopefully remember that the prime means derivative. And so what we're trying to do is take the derivative of this integral. And so this has to do with knowing what a derivative and an integral are, and most importantly, what the fundamental theorem of algebra, did I say algebra earlier? I meant calculus. Okay, the fundamental theorem of calculus says that derivatives and integrals are opposite, that they undo each other. So if I take the derivative of this integral, it's going to get rid of my integral symbol, like it gets rid of all this and gets rid of the dt because that's part of our integral. What it leaves is the fact that we have an x here. That x is going to get plugged in everywhere that t is. And that's the only thing that happens, is that instead of it being negative t squared plus 4t minus 1, it's negative x squared plus 4x minus 1, and that's our answer. We don't need plus c because we were just completely undoing our integral. We don't have to worry about the number that was on the bottom, because if we integrated and then plugged in that number and then took the derivative, it would make it go away. So we just switch out the t for an x. So on 4, see if you can think of what that would be, and then I will tell you that that would be negative sine x. And that's it. That's your answer. Now, into this whole differential equations situation, we have some easy to solve differential equations. And the reason I say easy is because this is as easy as it gets. All we're doing is saying there's just x's on the right side, so we don't have to even cross multiply or anything, although we could and we would still end up with the same answer. But all we're really doing is saying, well, let's take the integral of both sides of my equation. When I take the integral of dy over dx, which is a derivative, I get y. It undoes the derivative. It makes it go backwards. And then I just have to figure out what the integral of 1 over x plus 2 is by remembering my integral rules. The rule is that when x is on bottom without a power, it turns into a natural log of the bottom. And since there's not a number in front of x, and it's not x squared or anything like that, then we don't have to worry about using u substitution. It's just ln of absolute value of x plus 2. Since we're taking the integral, we put plus c because there's probably, or could be, a constant there that we don't know about right now that maybe later on we could solve for if we wanted to. So on number 6, we're going to take the integral of both sides, and that gives us y equals the integral of negative 3 sine x. So you have to remember what the integral of sine is. The integral of sine is negative cosine, and since the integral of sine is negative cosine and we have a negative 3 in front, it's going to make it positive 3 cosine plus c. we're going to keep going with the same kind of problem now. We have dy over dx equals 4x plus 1. So we're going to do the integral of each side. And we just have to say, okay, what rule am I going to use for 4x plus 1? That's the power rule. So this has a power of 1 right now. We're going to add a power, which gives us 2. And so if it's a 2, and then I would have to divide by 2, that's 2x squared. And then this is going to get an x put with it, so it's plus 1x, and then good old plus c. Then here on 8, I'm going to take the integral of both sides, but this is going to require us to do something special here. This is the power rule, but it's not immediately obvious that it's the power rule because we need to move the x squared from the bottom up to the top. To do that, we have to give it a negative exponent, and then we use the power rule. So if I add 1 to a negative 2, I get negative 1. And I have to divide by that power, so I divide by negative 1. Well, I'm going to rewrite that on my answer by saying, okay, 3 over negative 1 is a negative. 3 is going to be on top, and then I'm going to move this back down to the bottom so that it is negative 3 over x plus c. Now, this is the same type of problem, except it's on the earlier section it said find the general solution, which means that plus c was an okay way to leave it, but now this is saying to find a particular solution that satisfies the initial condition they gave us. And so the difference between a general solution and a particular solution is that a general solution works in general for some value of c that we could find if we wanted to, but a particular solution is only the solution for a particular case that they've given us. So we have like 3 of these to do. It's going to start the same way as our last ones did, where we integrate both sides. And this actually is really close to what we just integrated a second ago. We add a power, so it's x squared, divide by 2, so it's negative 2x squared. This is going to get an x because it doesn't have one. It's like you get an x and you get an x. And you, maybe it's not like that. Now, this next part is telling us what to plug in so that we can find c. And so it's not that super difficult to do. Just remember that this is like back in algebra when we had f of x equals something. And what it is that this is your x value because it's x, and this is the y value that would go with it because you have a function that you're plugging x in and getting y out. So they put y of 1 equals 0. I don't know why they put y of 1. Oh, wait, it's because this is a y. So they were saying, you know what, never mind. So what we want to do, though, is we want to say, all right, this 1 right here is x, and this is a y value of 0. I'm going to plug that in. This is 0 equals negative 2 times 1 squared plus 3 times 1 plus c. Now this is a little weird because we're used to just like solving things for x, but we don't need to solve for x. We want it to be x's in our equation. What we need is c. So we plug in y, we plug in x, and we're going to work this out and then make sure that we remember that we're solving an equation, so we have to use those rules. This is 0 equals negative 2 times 1 is negative 2. 3 times 1 is 3. Well, I have to do negative 2 plus 3, which is 1. So 0 equals 1 plus c. That means that c has to be negative 1. So my answer, I have to actually go back and rewrite this and say this is y equals negative 2x squared plus 3x minus 1. Because c was negative 1. So at the end there, that number is negative 1. Oh no, number 10 looks terrible. Look at that last part where there's like a fraction, and oh, I'm sure it'll be fine. Okay, so what we want to do to start off here is something we did earlier. Sorry, I couldn't figure out where my cursor was. All right, so we want to use the power rule. We're going to move this up because we're integrating. Move it up, and so we are trying to figure out negative 3x to the negative 4 with the power rule. So that's going to give us negative 3x to the, when I add 1, I get negative 3. So I'm going to divide by -3. That's pretty convenient. Those will cancel out. So that means that y equals, I'm going to move the x to the -3rd down to the bottom, but there's not a number left, so there will be a 1 on top of x cubed plus c. And so remember, this is our x value, this is our y value. We're going to plug in and find an answer. So 55 over 27. I'm sure this will work out. I'm not worried. 3 is an x, or 3 is x. X is 3. So what's great here is 3 cubed is 27. And so that means we've got 55 over 27 equals 1 over 27 plus c. And then to solve this, we're going to subtract 1 over 27. And 55 over 27 minus 1 over 27, that's not so bad because they've already got common denominators. That's 54 over 27, which simplifies very nicely into 2. So c is 2. We go back and plug that in, 1 over x cubed plus 2. One more like this, but also kind of different, because if you see this in your initial condition problem, that should help you remember that, okay, my x is on bottom, so that's going to make this be a natural log problem. Otherwise, well, I mean, I guess it wouldn't have to be, but then you'd end up with c having like a natural log for an answer, and that sounds terrible. So let's integrate. And the x is on bottom without a power, so this is natural log of the bottom plus c. So this is x, and all of this is telling us our y. So we've got ln of 5 minus 3 equals ln of -2 minus 3 plus c. Now, this is where those absolute value bars come in and are important, because if they weren't there, our natural log would have an error right here. But as is, it's -5, and the absolute value of -5 is regular 5. So we've got this, and you may have already decided to reach for your calculator, and that would work actually. You could find natural log of 5 minus 3 and then subtract natural log of 5 on your calculator, and it should tell you the answer. Or you can say, well, if I subtract this, that's going to cancel out that natural log on each side, which sounds great. That's -3 plus c. No, it's not. It's -3 equals c. There's a difference there. -3 equals c, so y equals natural log of x minus 3 minus 3. And just so we're all clear, you can't put those -3's together because one's inside of natural log, one's outside. It's like a house or something, like there'd have to be a door. Okay, never mind. Next section are separable differential equations. Now, adding that word may make it seem super intimidating, but in reality, these are, again, some of the easiest differential equations to solve. You know that you need to use this concept of separation of x's and y's when there's y's on the right side. That's what separable means, is that we can separate and make y be on one side, make x be on the other. We're going to do that by a good old skill we learned in Algebra 1, cross multiplication. So that's going to be y squared dy, 3e to the x dx, and we want to integrate both sides. And so it matters here that our y's are together, we have y squared and dy, and that our x's are together, e to the x and dx. When I integrate the left side of this, that's going to be the power rule, so y cubed over 3 equals, and then the integral of e to the x whenever there's not anything else in the exponent with x is just e to the x, so it'll be 3e to the x. Now, technically at this point is where we should put a plus c on one side or the other. Doesn't matter which, and we only need one. You don't need to put plus c on both sides. And so when we do plus c and then solve for y, we would times by 3 on both sides to get rid of that. And so we would times this side by 3 as well. And that's going to give us y cubed equals 9e to the x plus, now if you think about it, we don't know what c is right now, and we're going to times it by 3, which just gives us another constant, so we could just leave that as c still. And then we're going to keep going by cube rooting both sides. And so y cubed, nope, not cubed anymore. So y equals the cubed root of 9e to the x plus c. Now, as a disclaimer, I kind of glossed over the plus c thing in my class that I'm teaching. And so if you're in my class right now, and we just put the plus c at the end, at the very end, and so that's totally cool. Technically, it is a little bit more complicated than that, because you're supposed to put the plus c as soon as you've taken the integral, but that would be the correct answer. But if you have the plus c outside, I'll be cool with that. All right, we want to do this next one, and this one's a bit trickier because of that pesky 2y that we've got there. We start off just cross multiplying. And so I forgot to write dy there. We're going to take the integral of both sides. And so it's easy to forget if you're not doing it all the time, but this being 2y is a big deal. This is u substitution if you want to think of it that way. Like, for some people it's really easy to just gloss over, but essentially we're doing u substitution where we're saying u is 2y, du is 2, because it's the derivative of 2y, which is just 2. And so what we're really trying to figure out is what is the integral of e to the u, but oh wait, there's a 2 here and there wasn't here, so we have to divide by a half. Then we plug back in what u was, and so this is 1/2 e to the 2u. Now that was a kind of a big long explanation for the fact that if there's something in the exponent that's just a number, like just a coefficient for y, you're going to end up dividing in front. If this had been a 3, you would have put 1/3. If it had been a 4, you'd put 1/4. It's not, it's a 2, and now I've marked all over it, but it's a 2, so we need this 1/2. Even if at some point later on it maybe will go away, we need that 1/2 to be there. Now, the right side is comparatively simpler because it's the power rule. So you add a power and get x cubed, divide by 3, which cancels out the 3. We've taken the integral, so we should put plus c, and then we're going to solve this for, this is not a u anymore, that's a y. Because I plugged u back and made it 2y. Sorry about that. So now we are going to first multiply by 2 on both sides to get rid of that half. And so we get e to the 2y equals, if I distribute the 2, that's 2x cubed. Now, just like earlier when we did c times 3 and we said, well, we can still call it c, we can do the same thing here. You don't need to put plus 2c because we don't know what c is, we just know it's a number. So it's still just a number. It's a different number than it was up here, but it's still a number that we can solve for. Now, here's something that is tricky. How do I get the y out of the exponent here? That requires us to do the natural log of both sides of our equation, and this has to do with inverse functions because e and natural log are inverses of each other. If I take the natural log of it, it makes the e go away, so that we're left with the exponent 2y, and that means the other side is ln of 2x cubed plus c in parentheses, and then we divide both sides by 2. And so y equals natural log of 2x cubed plus c over 2. So again, whenever we were doing this in class, if you actually have me as a teacher, we would have written the answer like this with the plus c on the outside. that is different a little bit, not a huge amount different. Like, depending on what C is, that may not really be that big a deal. But if you're if you're in a class and you're studying, like, that's the way to go. It's the way you have to kind of keep track of C the whole time. Let's do 2 more. So these are actually, I think, easier than the first 2 in some ways. We're going to cross multiply here, y squared dy equals x dx. These are both power rules, so yay, y cubed over 3 equals x squared over 2, although that's kind of unpleasant because they're both fractions. We want to solve for y. Since we're solving for y, we'll multiply both sides by 3 and get y cubed. Oh, I didn't put plus c. So we're going to do plus c and then times by 3. So this will be y cubed equals, that 3 and 2 aren't going to cancel or make this any nicer. So this is really like 3 halves x squared or 3x squared over 2. But just like before, 3 times c, we can just say is some other constant c. Then we're going to cube root both sides. And so when we cube root both sides, that the c will be underneath. So y equals the cubed root of 3 halves x squared plus c. And so if you're in my class, like, we would have put the plus c outside just at the end, just fine. On this last one, we've got, oh, secant squared y, interesting. Now, when I cross multiply, this gives me secant squared y equals 1 dx. Now, I forgot the dy again. Secant squared dy, you have to think about what is the integral of secant squared, and it's tangent, and so this will be tangent y. The integral of 1 dx, it doesn't have an x, so it needs an x, and we'd put plus c because we've taken the integral. Now, this is tricky. This has to do with the same idea as earlier when we did e, or we had e and we did ln. How do you get rid of a tangent? I feel like there's a punchline there if we really work on it. How do you get rid of a tangent? You make him live in a cave? I don't know. Anyway, so the way you get rid of this tangent in front of y is you take the inverse tangent of both sides. And so the inverse tangent is tangent to the -1. On this side, it makes that cancel and gives you y, but on the other side, it's going to be inverse tangent of what's on that side. This is not because we are dividing by tan. That is not a thing you can do. It's because we are saying, let me undo tangent and take the inverse tangent of both sides. And so that's your answer. Now we've got slope fields. So when we have slope fields, they are giving us a differential equation, and we're trying to, at each of these dots, which there's 5 in each row and column, so there's 25, at each of these, we are trying to draw the slope that this differential equation would have. The way we do that is by plugging in x and y values into this side of my equation. So for instance, I like to start with like 1, 1, because it's so nice that they're both 1s. What we're going to do is plug in x and y to this right here, although this only has y and not x. So all I really need is the y value, which was 1. When I plug that in, I get -1 over 1, which is -1. So at 1, 1, I'm going to draw a slope of -1, which is a negative slope that's like evenly, like not super steep and not super not steep. It goes up and over 1, so that means that it is basically like a 45-degree slant happening. And so that's one of my 25 points. And so if you're thinking about this and saying, oh, I have to do 24 more like that, you should be able to figure out a pattern so that it's a little bit quicker, because on this, all that mattered was the y value. So everywhere that y is 1, we should get the same thing, -1. And so y is 1 at all of these places. And you have to just do the best you can as far as like making them look the same and making them look like -1. Just FYI, it's probably not going to be perfect, but you have to just do the best you can. On the other side, we could do, when y is -1, that's going to make our negative cancel and give us a +1, which is the same kind of slope, just going the other direction, the positive direction. And we can do 0 because we do need to do this, the x-axis. And so if you think about that, when y is 0, that's -1 over 0, which is undefined. And an undefined slope is a vertical line. It's like that because we're going up 1 and we're not going over at all. So if that helps you remember, you're going up 1, you're not going left or right, although those are some really bad vertical lines, sorry. But if you remember up 1 over 0, that's one way. Another way that you may have been taught it back in Algebra 1 is that a skier on an undefined slope has an undefined amount of fun because he has to go really fast, as opposed to a skier on a line with 0 slope who would not have much fun at all because he or she would have to push himself the whole way, which is a lot of work. So that's a way to tell the difference between those. Now we got to do 2 and -2. So for +2, that's -1 over 2, which is -1/2. That is less steep than what we did before, and so it's going to, you're going to try to make it look less steep than what you had right below it. And see, that was not good on my part right there. But I'm just going to move on because I don't really know how easy it is to erase these. Okay, no, I'm going to go and erase it. See it? Oh my... So the last one, the -2, you'd have -1 over -2, and the negatives would cancel, giving us +1/2. So it looks like this line, but going the other direction. And again, if you're like a perfectionist and it bothers you that your lines aren't the same or that they don't look quite right like the actual slopes you want, you're probably at some point just going to have to try to just leave what you have alone and move on. Whenever it just has an x, then all that really matters is the x value. And so when x is 0, for instance, our slope will be 0. X is 0 along the y-axis. So that's here and here and here and here and here. When x is 1 and we plug it in, we get 1. So that's 1. When x is -1, that's going to be -1. When x is +2, that's going to be a steeper slope because we've got to go up 2 and over 1. Again, it can be really hard to make these 2's all look the same and different from 1 or 3 or 4 especially, but you just do the best you can. And really, like whenever someone's looking at this and grading it or interpreting it, it's really more about like backing up and looking at this shape. For instance, what this is doing is it's showing us actually what the solution to this differential equation is, because if we actually work it out, we would get x squared plus c. And so what's happening here is we've got parabolas. We don't know what the y-intercept is because that's what plus c is, but we know that we have parabolas. That's what our shape looks like. Over on 16, it'd be a parabola that was opening to the left because it's a y instead of a x. I just ruined that. So we're going to move on before I erase everything again. All right, now 18 and 19 both have x's and y's, so it's going to require a little more thought process on our part because we have to plug in x and y. So 0, 0 is an easy place to start because 0 times 0, even negative, is still 0. So 0, 0. And in fact, anytime x or y is 0 should be a 0 slope. So we can fill in like a bunch of them that way. Thanks to that little handy dandy situation. Then from there we will have to think more, probably like 1, 1. You plug ones in, you multiply them together, and then make it negative, and so you get -1. And then down here, 1 and -1 multiply to get -1, but you make it negative, so that's going to be +1. Then you might realize just from the way things work that that should be a -1 and that should be a +1. And a similar thing is going to happen in our quadrants of the pattern that we just saw here of like a mirroring thing going on. For instance, 2, 1 gives us -2, which means that it's steeper, which over here it'll be opposite. Down here it'll go this way, and then down here it will go this way. And you can plug the numbers in and multiply them out and actually see that for sure. But if you realize there's a pattern and you feel comfortable sticking with it, then do that. This is also going to be a -2 up here, and so we can fill in those. And then the last one, which is the most annoying one, is 2 times 2 is 4, and we're going to make it negative. And how in the world do you make -2 and -4 look different? -4 basically is almost like a vertical line comparatively. Try not to make it actually be a vertical line, but it looks super, super close. So there we go. That's that one. Then -y over x is going to be different than that. One thing is that where x is 0, 0 is on bottom, and so that's undefined, and that happens along our y-axis. But in the middle here, where we have 0 over 0, because y is 0, if we had to put something there, I think undefined would be the better thing to put there, but I'm not really sure that we should put anything there. I think we should just skip over 0, 0 personally, because it's trying to suggest that it's 0, but it's undefined, but they're the same number on top and bottom, so maybe it's really 1. So let's just either put an undefined line or nothing at all there. When y is 0, which is on the x-axis, our slope is 0, because 0 on top is 0. And then just like when we were multiplying, when we do the combinations of 1 and 1, we'll get slopes of 1, because when we divide them, we'll get 1. But it is negative y over x, so it'll be -1. This will be +1. This will be -1. This will be +1. Then we're going to do 2, 1. And so it matters that you pay attention to what's on top. Y is on top, x is on bottom, so that's -1/2. And then this will be +1/2, -1/2, +1/2. If we do 2 and 2, that is going to give us -1 again, because they cancel out. So we can do that on the other side, and then it goes the other way. And then we just need 1 and 2. So now y is 2 and x is 1. So that gives us a -2. So it's going to be steeper. So there's slope fields for you. Now we're going to do some good old word problems related to exponential growth and decay. Now, when we're doing exponential growth or decay, we can actually do it with money when we're compounding interest continually, like is in this problem, or we can do it with things like bacteria that exponentially grows, or we can talk about substances exponentially decaying. But our formula in general for that is y equals y0 e to the kt. Or you could think of it like a equals a0 e to the rt. Specifically for money, you might see a's instead of y's. They're really the same formula. What we do is we take the initial value, which if you read this problem, 19,000 is what we're starting out with. That's going to be our initial value. And then we want to know, if we read through, how long it will take for the investment to triple. And so there's a couple different ways to do this, but probably the easiest way is to say, well, what is triple of 19,000? So you multiply it by 3, which gives you 57,000. And then we do e to the, make sure you change this to a decimal, because right now it's a percent. You don't just put percents into problems. That's not really a thing. You always have to change them to decimals, and we change it to a decimal by moving the decimal 2 places to the left. So this is not 0.75, that'd be 75%. It's 0.075, and then t is up here. To solve this, we are going to divide both sides by 19,000, and that's going to lead us to actually a different way we could have started this problem, which is the fact that they told us that this was supposed to triple meant that there should be a 3 on the left side whenever we don't have anything in front of e. And so we could have skipped that initial step if we realized that that was supposed to be 3. It's not a coincidence that we were tripling and this is a 3. It's like math that's supposed to happen. So if you're doubling, this should be a 2. If you're halving, this should be a half. Things like that. Now to solve this, we need to get rid of e, which we did that earlier on a problem. We're going to take the natural log of both sides. So natural log of 3 equals our exponent, 0.075t. One way to think of it is like, it's like you're trading the e on this side to put an ln on the other. It's like making it even or something. So we can put ln of 3 in our calculator and then divide by 0.075. And this is definitely on these problems where you want to utilize being able to do second and the negative button to put your answer in, so that you don't have to round, because rounding creates error, which is bad. It wants us to round to the nearest hundredth, which is 2 decimal places, and so this is 14.65. If you go back up and look at the time, it says hundredth of a year, so it must be in years. So 14.65 years is our answer. Let's do another one. What will be the amount in an account with an initial principal of $5,000 if interest is compounded continuously at an annual rate of 4.75% for 7 years? So they want to know what the amount is. If we start with 5,000 at 4.75%, so 0.0475 for 7 years. You just have to type this into your calculator exactly how it looks. There's an E button on the left side in the middle-ish. You do second and then press natural log and it puts E and gives you an exponent. And when you type it in, you get an amount of 6,972.25. So that's a pretty easy problem as long as you realize, oh, I don't have to actually solve for anything. I just need to plug this in. How long will it take a sample of radioactive substance to decay to 40% of its original amount if it decays according to the function blah blah blah, where t is the time in years? This might actually be easier if they hadn't given us 450, because the 450 and the fact that it's 40% here may throw you off. If they didn't give us 450, we could put 100 here and 40 on this side, and when we divide it over, that would give us 0.4, which is what we want. But because they gave us 450, we might get stuck and be like, I don't know what to put on the left side. Well, you'd put what is 40% of 450, which is 180. So 180 equals 450 e to the negative 0.09t. Or you could have said, well, I know no matter what that when I divide 450 over, I'm supposed to get this percent, 0.4. So you could have skipped and said, okay, I know it's going to be 0.4 e to the negative 0.09t. Take the natural log of both sides, and then divide by negative 0.09. Type that into your calculator, and you get 10.18 years. Now we've done some money, let's talk about some good old bacteria. This says that bacteria is being grown under ideal conditions in a laboratory so that the population increases exponentially with time, which actually is kind of reassuring that maybe bacteria doesn't always grow in ideal conditions, so maybe it doesn't always grow exponentially, because that sounds like a terrible situation to have on a regular basis. That's not really the point. At the end of 2 hours, there are 3,000 bacteria, and at the end of 5 hours, there are 32,600 bacteria. How many bacteria were present initially? They didn't give us an equation, so we're going to have to make up our own using either formula that I had earlier, y equals y0 e to the kt. The problem is that we are trying to find the initial value, and we basically, if you don't know k in a problem to start off with, that has to be what you find first. And so we're going to do that by being super duper crafty. We're going to say that why don't we pretend there's another situation here where 3,000 could be the initial bacteria and 32,600 could be the final number, and then we're trying to find k, but t would be how long it took to get from 3,000 to 32,600, which is 5 minus 2, which is 3. And so that's going to let us find the k, the way this is growing, how fast it's growing, and then we'll plug back in so that we can figure out what what y of 0 is. So we need to divide by 3,000, and we get an uneven number, like it doesn't divide evenly, 10.87, which is rounded, and then e to the 3k. We're going to take the natural log of both sides. So this is where you're going to use the second answer button on your calculator so that you don't have to round, because what we want to do is natural log of whatever this was when we divided it. So natural log, and you do second answer, close your parentheses, and then divide by 3, and that gives us k. K is 0.7952, and then 3's just keep repeating. You don't have to necessarily write all of those down, but when you're finding k first, you need to have at least like 3 decimal places. You don't ever want to round k to a 10th or even a 100th, because when you plug that back in, you've just made a really, really big difference. Because remember what k is. K is a percent. So if I round this to 1 decimal place and then change it to a percent, that's 70%. If I round to 2 decimal places, that's 79%. Now, let's pretend that those were your grades. Is there a difference between a 70 and a 79? I think so. So then 79.5%, if I round to 3 decimal places, well, there's not a huge difference there. Oh, wait, 79.5 is a B, 79 is not. So maybe there is a big difference there. So that's why we should always round to 3 decimal places, especially when calculating grades. Anyway, now that we know what k is, we are trying to find the initial amount present, and so we can use either 3,000 or 32,600, but we're not going to use both. If you use 3,000, and we're trying to find y0, k is 0.79523, repeating. Again, you don't really need all of those, but hey, it's whatever. T is the 2 hours it took to get us to 3,000. If we had used 32,600, we'd put in 5 where that 2 is. Now, you may be like, how do I solve this? All I need to do is take this right here, which is a number, and divide it over to the other side. I don't really feel like writing that out again. 3,000 divided by e to the 0.79523 times 2. Again, you can use the second answer button to help you. So this ends up being 611 bacteria. It doesn't tell us what to round to, but bacteria is, I'm guessing, like people, where you typically don't want to talk about like half of a person. We wouldn't have half a bacteria, so it's 611 bacteria present initially because we rounded to the nearest bacteria. Now, if that bacteria problem wasn't so much fun that now you're not watching this video anymore, we're going to talk about Newton's law of cooling, which happens to be, in my opinion, one of the coolest things that we can do in math, because Newton's law of cooling says that things that are hot, when they're in an environment that is cooler than their temperature, they will cool in a way that is similar or is actually exponential decay. And the thing that's really cool about that is that we can use that to predict things, not predict. We can use it to figure out if at a crime scene, we're going to take the temperature of a dead body when you get there to start investigating, and then take it whenever you are about to leave. And if you know how long it was between there, you can estimate when the body was at a normal body temperature, which is when it died. So when you watch those crime shows on TV where they say, well, the time of death is probably around 10 to 11 or something like that, one of the ways you can calculate that, because there are a lot of different things that go into it, but one of the things that can go into that is saying, well, when was this body a normal temperature? Now, we're not going to, do some morbid dead body problem. We're going to just talk about like coffee and lasagna or a casserole, something like that. Some nice food. We're going to talk about it cooling, which you may find more boring, but it won't give you nightmares, so that's good also. The formula for Newton's law of cooling is T minus Ts equals T0 minus Ts e to the negative kt. Now, this formula is actually really similar to our formula for exponential growth and decay. What we have to do, for one thing, is define what these are. T of S is the temperature of the surroundings. So like your room temperature, or in this first problem, the freezer is going to give us the temperature. TO is our initial temperature, or T0. And then K is a constant we're going to find. It's negative in this formula because we're cooling, so it's going to be decay. When we're decaying, we have negative exponents. Then we have little t is time, that's past, and big T is the temperature. That's not how you spell temperature. Is the temperature at little t. So what we have to do in these problems is they're going to tell us what it starts out as, what the room temperature is. They're going to tell us what temperature it is after a certain amount of time, and then ask us something else. The first part of that means they've given us the information to figure out what K is. And then once we know what K is, we're going to have to go back and plug in to figure out what they're actually asking us. So in this example, our cup of coffee starts off at 110 degrees, so that's T0. Then it's placed in the freezer, which is going to give us the room temperature, if you want to think of your freezer like a room, very, very cold room that you would not want to be in, because I feel like you'd freeze to death. So TS is 0. Oh, but then somebody could use Newton's law of cooling to find out when you died. Never mind. After 10 minutes, so that's little t, your coffee is 60 degrees. And so that's big T. That's everything we need to find K. If you keep reading and are like, well, what are we going to do with this 15? It's going to come in the next part. So whenever I write this out the first time, big T is 60, TS is 0, so we could just put 60 there if we wanted to. Kind of like here, we could just put 110, because 110 minus 0 is 110. E to the negative k times t. So 60 equals 110 e to the negative 10k. This is no more difficult to solve than what we did earlier with exponential growth and decay. You're going to divide by 110 and then take the natural log of whatever that is, and then take that and divide by negative 10. And if you do this, like using the second answer button, you shouldn't have to round. You get for K 0.0606. Now that we know what K is, they want us to find what the temperature will be 15 minutes after the cup is placed in the freezer. So there's a couple things that are going to be different now, because this is going to be little t. We're trying to find big T. That's a question mark. Okay, trying to find big T. We changed little t, and now we know what K is. And so this information is not what we need anymore. T0 and TS are going to still be 110 and 0. So we're going to have big T, which we're solving for, minus 0 equals 110 minus 0 e to the negative k T is 15. And so then we're going to solve this for what big T is. Which, if I do that, gives me 44 degrees Fahrenheit. And so if we want to solve that, all you have to do is type this into your calculator right here. 110 e to the negative 0.0606 times 15. If this wasn't minus 0, we'd have to add that number over to the other side after we've plugged in everything else. Since it's 0, it just goes away and doesn't really matter. So it's 44 degrees. Let's do another one to see what we've learned. And so you might try this on your own first to see if you can get the answer, and then then make the video play again so that you can see if you're right. So this starts off with T0 as 400. The room temperature is 76. After 5 minutes, which is little t, the casserole is 321, which is big T. Then we want to find out when its temperature will be at 200. Now, let's set this up. It is T minus TS equals T0 minus TS e to the negative k times 5. We're going to solve this. I feel almost like I should put in a disclaimer here, by the way, that I made up these problems, so I don't really know if this is reasonable for how things would cool or whatever, or if casseroles are even cooked at 400, because I'll be honest, I'm not really a casserole cooking kind of girl. So we get this, we're going to divide by 324. And I get 0.756 equals e to the negative 5k. So then we take the natural log of both sides. And that gives us 0.055897. I'm pretty sure that's how I wrote it out, because after 7 it was like a 0 or a 1 or something. So that seemed like a nice place to round. But you could really do a couple less decimal places and be fine if you wanted to. Now let's find out when its temperature will be 200. So now we want big T to be 200 and little t is what we're trying to find. So 200 minus 76 equals 400 minus 76 e to the negative 0.055897 t. Now this is going to be more involved to solve, but again is like what we did earlier. So 124 equals 324 e to the, that exponent. We're going to divide both sides by 324 and get 0.383, which we'll have to take the natural log of, and since we're taking the natural log of it, that e won't be there anymore. We'll just have our exponent, which will divide by k. If you are being super crafty, you could do this without any rounding at all. Actually, maybe you don't really have to be that crafty, but until the end, obviously. At the end, we're supposed to round to the nearest minute, which is 17 minutes. That's our answer. Hope you have enjoyed this review. Happy mathing.